This video is sponsored by Brilliant, but more on them at the end of the video. Hello there and welcome back to another video. In today's video, I am on travel, so I'm recording this on a handheld microphone in a random bedroom on a bed, so I apologize if the audio is subpar. But either way, in today's video, I want to take a bit of a deeper dive into the computers that we all know, love, and use today. We probably all know that computers are made up of components such as CPUs, which can look like this, or if you go back 26 years, this. They've also got components such as RAM, which I think everyone watching this channel is well familiarized with. And sometimes they even have dedicated graphics processors like this RTX 3050 6GB. Of course, computers are also made up of other components like motherboards, power supplies, cases, and storage drives. But the main processing components of a computer are these three. But what makes up these components? The answer I'm looking for isn't silicon, though that is technically correct. The answer I'm looking for, instead, is transistors. To put it simply, a transistor, such as this 2N2222 transistor, is a simple, electronically controlled switch. These awesome little devices are a lot more complex than this, but we're just going to operate on basic principle today. Anyway, I can use this transistor with a button to control an LED in a super simple circuit like this. And although this is a bit useful, it's really nothing special. When transistors do get special though, is when multiple of them are combined in different combinations to form what are known as logic gates. For example, I built up this small circuit here with 2 transistors and 2 buttons, which forms an AND gate. This gate takes the 2 inputs from the 2 buttons and only turns the LED on when both of the inputs are also on. So, if one input is on and one is off, the LED is off too. And if both of the buttons are off, then the LED is still off. Then, I reconfigured the 2 transistors to form a different kind of gate, an OR gate. The OR gate takes the 2 inputs and basically just passes them straight through to the output. So the only time that the output is off is when neither of the inputs are on. If one input or both inputs are on, then the output will also be on. The only reason that this is different than 2 wires that get conjoined into one is because this gate doesn't let the inputs feed back into each other, so if one input is high, the other input doesn't get pulled high too. The final gate that I built out of discrete transistors is this one, the NOT gate. This one differs from the other 2 gates that I showed because this gate doesn't work on a 2 inputs and 1 output setup. This gate only has 1 input and 1 output, and you've probably gathered from the behavior of this gate that the output is the opposite state of the input. If the input is low, the output is high, and if the input is high, the output is low. Now, these 3 logic gates are the basic building blocks of logical expressions, and other logical expressions such as exclusive OR, NAND, NOR, and several others can be made by combining these 3 gates in different ways. Now, building all of these gates out of discrete transistors is really inefficient. While it's super cool, especially when you check out the people on YouTube who have done this with neat breadboard wiring and have made massive contraptions, there's still no way of going around this fact. Thankfully, all of these logic gates can be had in the forms of simple ICs, and I have several of the ones from Texas Instruments' SN74HC series. For example, here's an SN74HC08N, which as you can see is an AND gate IC. This chip has 4 separate AND gate circuits in it, which can be super useful for programming logic or making a simple computer. I can switch this chip out for the SN74HC32N, which is an OR gate IC, and it behaves exactly as expected. Finally, I have the SN74HC04N, which as you might have guessed by this point, is a NOT gate IC, and it reverses the state of its input on its output. Plus, this chip has 6 separate inverter circuits in it as opposed to the 4 on the other chips, because each one only has 1 input and 1 output pin. Now, I did actually just lie to everyone watching this video, because that actually wasn't the final logic gate IC that I want to show you today, or that I have. I actually have one more, which I really want to show you, the SN74HC132N. This is a quad NAND gate IC, which exhibits its own properties as its own operation, but it also has another trick up its sleeve. The NAND gate is a super versatile gate, which can actually act as any other kind of logic gate when grouping, most of the time, multiple of them together in different configurations. Don't believe me? Well, here's the NAND gate on its own. You can see that the output is high when at least one of the inputs is low and only goes low when both of the inputs are high, just like an AND gate whose output is running through a NOT gate. Now, let's try combining a few of the NAND gates in this IC according to this schematic and see how the newly created logic gate behaves. Well, that's interesting. The output is low when both inputs are low, high when one of the two inputs is high, and low again when both inputs are high. Yep, that's a brand new logic operation that we just created with multiple NAND gates. This is what's known as the exclusive OR or XOR operation, and it's super useful for making computers. This operation can also be made with the standard 3 NOT, AND, and OR gates, but we've just made it with a single gate type. How about we try reconfiguring these NAND gates again, and let's try what happens according to this schematic. Well, now we've created an OR gate, and this just keeps going for all of the other kinds of logic gates like AND, OR, NOR, and more. You can really see how the NAND gate is one of the most versatile types of logic gates through this behavior. And one good example of the NAND gate combinations going even further than just the regular logic operations is this circuit that I have built up using a total of 5 NAND gates. This right here is a data latch, which has 2 inputs, a data input and a store input, and of course it has one output. When data is put on the data input, which can be either a high or low signal, indicating either a 1 or a 0, the data latch's output will not update until the store signal is pulsed high. Then the data latch will store the value of the current data that it has on its input and won't change the output value until the store signal is pulsed again with different data. As long as the store signal is held low and isn't pulsed, the gate will completely ignore what's happening on the data input and will only output the last data stored. These data latches, in combination with some other logic, can be combined to create a register circuit. Register circuits are incredibly important to computer CPUs and are used for every instruction that gets executed as it travels throughout your chip. Now, this video is not a full tutorial of dealing with binary and logic gate-based circuits because frankly, I am not knowledgeable enough about that part of this subject to say anything on it in my video. And on that part of this video, I would like to mention at this point that Sebastian League's videos have been incredibly helpful for working on some of the circuits in this video, and in particular, this final bit of the video, where I'd like to show you the design for a project where I've utilized the concepts surrounding NAND gates and other logic gates to design a small computer that's built fully out of NAND gates. So I'm going to pass over to Live Audio Me to talk to you a bit about this circuit because I think you'll find that super interesting. All right, so it is Live Audio Me here, and I'm just here to talk a little bit about the design that I made, just because I am pretty happy with it, and I think it's got the potential to be a really cool device if I was to actually build it. Now, I'm not sure if I will, because it uses a lot of these logic chips, and I priced these out on Mauser Electronics, and it'll be like not 150, sorry, 100. It's like 150 chips, and I'd probably buy a little more than that. So it would be close to $100 of logic ICs, which is a lot, and I can make that happen if people are interested, but if it's a video that's going to get like 300 views, I don't really want to spend that much on it. So if you are interested in this, please let me know, and if people are interested in this, I will do it. Happily. I would actually really love to do this project, but you have to let me know and make it worth the time and money, because this will be expensive, and the board for this will also be expensive. Now, anyway, let me talk a little bit about what exactly I did, and I'll actually stay in the board view for a sec here, because right here, you can see this right here is one of the 2 registers in this small computer. And this small computer can take 2 signed 8-bit integers, and it can either add them or it can subtract them. And so I believe because they're signed, that means that the range for each number is 127 to minus 127. Correct me if I'm wrong, but I think that's the actual range. That's also the range on the output. So if you do 127 plus 127, it will overflow. So it's not a very advanced computer, but it will actually tell you that it overflowed, which is really awesome. And yeah, it's just a small 8-bit computer that can handle signed numbers. I think it can also do unsigned, actually. You just have to read the binary differently. I'm not 100% sure. Negative numbers in binary is something that I still need to learn more about. I based this heavily off of the information in those Sebastian League videos that I mentioned earlier, but I think this is a really awesome design, and I'm really happy that I was able to come up with it. And it is built entirely out of these SN74HC132N chips, with the exception of obviously some pull-down resistors, switches, LEDs, and the clock circuit, which is just a 555 timer. So yeah, we have the two 8-bit registers, and then over here is the ALU, which can just add the two numbers, and then this vertical line of XOR gates is there to invert one of the number's signs if we choose to subtract. So instead of having addition and subtraction operations, we have an addition operation and the ability to flip the sign of the other number if we want to subtract, because that will be the same as subtracting. And so all of that feeds out into just a really simple 8 LED display with another LED for sign to indicate if it's negative, and another one for overflow. And then the inputs are set with 8 switches and another one for subtraction mode. And what you do is you set your number, and then you go over here with these push buttons and you select if this is digit 1 or digit 2. Input 1 or input 2, and then you can press the button to store it into the register. And once it's stored into the register, the display will display what's in that register based on which digit you have selected. That's what this circuitry here does. It switches between displaying the output of register 1 or register 2 based on whichever digit you're on. That is the small computer design, and I think it's really cool. If anyone is really into this stuff in the comments and you see any flaws in this, or anything cool that I could do, please shoot me a comment, because I'm really digging this, and I would love to hear more from someone who's way more experienced at this than me. But in any case, I'm going to flip us back over to VoiceOver to finish out the video. I think that this has the potential to be a super awesome project, and if you'd like to let me know that you'd like to see me build it, put a comment down below. It will be quite the production to make this thing come to life, but if there's significant interest, I will absolutely do it. And finally, I want to take a moment to really appreciate the countless engineers, mathematicians, and other people who have somehow managed to make the computers that we have today. Thinking that every single computer we have today is just a massive combination of these logic gates working on physical electronic signals is just insane to me. All of the binary and logic systems that computers work on are just brilliant. And if you want to learn more about them and how they work, I'd recommend that you check out today's video sponsor, Brilliant. Brilliant is an interactive learning platform where you can learn about all kinds of different math, science, data analysis, and computer programming topics. I've been using Brilliant for the past while, and I honestly love the way that the platform is laid out and presented. The way that it gives you only small bits of information and then quizzes you on that information immediately afterward really ensures that you understand each step of what you're learning properly. Brilliant was a key factor in the creation of this video because I worked through their whole digital circuits course, which not only taught me a lot about logic gates, but also actually inspired me to sit down and learn more about how computers work on the logic gate level. It finally got me out of my seat and working with some of the logic gate ICs that I had bought a long time ago to mess with some of this stuff and had never ended up touching. If you'd like to try everything that Brilliant has to offer for free for 30 days with 20% off a premium annual subscription, either scan the QR code on screen or check out the link in the video description. Thank you again to Brilliant for sponsoring this video, and I highly recommend that you check them out if you're interested in anything math or computery. Well, that's all that I have for you in this video. I hope that you were able to at least enjoy it and maybe even learn a thing or two. In any case, I hope to see you next time. Goodbye.